Alright, let me start this video by saying once again we're about to play with some pretty high voltages. So don't try running these tests at home. Again, it's very dangerous. I've been working around high voltages for several years and I'm quite comfortable in running these tests. So let's get on with the video. Hope you enjoy it. Hello again and welcome. There's a YouTube channel called Voltlog that I watch from time to time. And recently he made a video where he took a bunch of pocket meters, not this one exactly, but basically he had hooked up a insulation tester to each meter and he was trying to use that as a high voltage source to stress the meter's inputs. And what ends up happening is, of course, when he puts it into the resistance range, it appears his insulation tester basically puts out no voltage.
To test these ratings, you will need something specialized, special equipment, which is called a transient voltage generator, capable of reaching those levels. I don't have something like that, but I have this guy, the Bryman 887 installation multimeter, which can generate a voltage of up to 1 kilovolt and measure if the insulation breaks. It might not be all that relevant to measure the insulation of a multimeter because it could still fail and remain isolated between the two inputs, but it's the closest thing I've got for generating a high voltage transient and applying that to these multimeters. And that should be similar to any kind of situation that you might encounter in practice, like for example if you are measuring some kind of circuit and that circuit fails, or if something behind that circuit fails and it sends a voltage transient. You might be in the ohms range, you might be in the volts range, it doesn't matter. The multimeter should be capable of absorbing that transient voltage without failing and without generating any dangerous situation for the user. Yeah, it's beeping because it's overloading, but look at how accurate it is measuring the voltage, same as the Bryman. So this has been very accurate throughout our tests. Not sure if it's due to calibration they use or maybe a more accurate multimeter chipset inside. Let's try the ohms range. So it's just showing overload. So yeah, I'm surprised. I was expecting at least the cheap Anhangs to maybe fail in some way, or maybe even the Mastec to fail in some way at the 1 kilovolt signal, but no, they survived just fine and they still measuring just fine.
So I thought it'd be interesting to repeat that same test, except using a little bit bigger power supply. So to start with, you can see I have my ESD simulator out. So the output of the ESD gun is attached to these two probes. Currently they're not attached to anything else except to the input of our attenuator, which goes off to this Bryman meter. So currently we're putting out 1156 volts. But again, there's no load. So you might remember this board here. This is a board that I used to model the BM869S when I had modified its front end. These are actually the transistors that I'd used to replace the ones inside of here. And again, we got that meter to survive at a 14,000 volt transient. So what I'm going to do is attach this to the output of our ESD gun. And let's go ahead and turn it up now. And you can see we only get roughly 12 volts or so out of it. Of course, that ESD gun is capable of putting out over 4,000 volts. And it can supply 15 amps, and it can do that in under 1 nanosecond. So why is it when I hook up this model of my Bryman BM869S, is it that the gun can only put out 12 volts? So if we look at the model for this system, essentially we have our battery, our ESD gun, and this is attached to two 1K ohm resistors in series. And that goes to a PTC, which is 1.3K. And that goes to a clamp, and then that goes back to ground. And you can see that on our board. Here's the input. Here's the first 1K, the second one. Here's the PTC, and over here is our clamp, and then this is the return path. course, there's other parts on this board as well. There's another 1K and another PTC that goes to this MOV, which goes in series with this MOV, which then returns to ground. Of course, these MOVs are rated for about 600 to 800 volts, so these aren't going to break down at 1000 volts. It's the same for this MOV over here. Of course, that's straight across this PTC to ground, but again, that's not going to conduct at these low voltages. So why is it that I told you that this gun can put out 4 kV, that we're only seeing 12 volts across this? Well, the answer is pretty simple. It's because the power supply that's used in this gun can't put out that much current. But I told you that this thing could put out 15 amps. So what's going on there? Well, the gun is made to put out a transient, which is a very short pulse. The time on this is about 5 nanoseconds total, and the majority of the energy is sub 1 nanosecond. It reaches this 15 amps peak, but it's only for less than 1 nanosecond long. What we're trying to do is put out a 1 kV signal and have it be DC, so indefinite. So it's not 5 nanoseconds now, it could be an hour. And essentially that's what's going on here. We've hooked up this gun, we've just basically connected this load, and we just can't supply enough current to put 1000 volts across this 3.3 k ohm resistor and then this clamp over here. Of course, this clamp is going to engage somewhere around 8 volts or so. So essentially all we have is our 1 kV source and a resistor to ground, which is at 3.3 k ohms. So that's quite a load. So with the Bryman on the right, we have it set to the voltage input. The Bryman on the left is set in the resistance mode. And if we look across the two inputs of the meter, we can see it's roughly 11 mega ohms. So this is a KDAC 20 mega ohm 1% resistor. I'm just going to connect this to the output of our transient generator. I'm going to use this second Bryman though. I'm going to place him in series with the resistor, and we'll measure the current through it. So again, I'll go ahead and increase the voltage. And you can see we're putting out roughly 1100 or so. Let's dial it back down. We'll keep the math simple. That's pretty good there. So that's roughly 1000 volts right there. So that's going to be 1000 volts divided by 20 mega ohms, or roughly 50 microamps. So we look at this meter and you can see it's only putting out about 9 microamps. So how come it's so low? You know, this meter is obviously reading 1000 volts. Let me just turn this up a little higher. So that's the power supply and the gun folding back. So if we select AC plus DC, so we can see it's 66.7 microamps right now AC, and the AC plus DC is 75.36 microamps. So even with that high of an input impedance, I still can't supply 1000 volts DC with this gun. First of all, notice that I've removed my attenuator, and that's because I'm testing at 1000 volts, and this meter is rated for 1000 volts. Again, we'll stay with our 20 mega ohm resistor. Let's go ahead and attach him, and we'll clip our Bryman directly across the resistor, and you're going to hear a contactor engage. There you go, we're putting out roughly 1000 volts right now, and you can see it's drawing about 150 microamps. Alright, so how come with our 20 mega ohm resistor are we reading such a high current? Well, again, if we look at the model of this, we have our power supply, and that's essentially going to our resistor, which goes to our 1 Bryman meter, which is set for current mode, back to our power supply, and again this is a 20 mega ohm resistor. But again, we have our second Bryman in parallel with this, looking at the voltage, and we said that the resistance of this is 10 mega ohms. So it's 10 times 20 over 30, or 200 over 30. So that's equal to 6.666 mega ohms. So if we take our 1000 volts and divide that by our 6.666 mega ohms, that's going to be 150 microamps. And again, if we re-engage this, you can see it's exactly what we're reading, 150 microamps. So let's try a little smaller resistor. Alright, so this is a 100k ohm resistor. So we take our 100k times the 10 meg divided by 100k plus the 10 meg is 99k ohms. Take our 1000 volts divided by that 99k, so roughly 10 milliamps. And again, E squared over R, or roughly 10 watts. So this resistor is going to get pretty hot pretty quick. It's not rated for 10 watts. Now 10 milliamps is higher than what a GFI would trip at. I think those are typically at 6 or so milliamps. With 1000 volts with this 10 milliamp, this is some pretty dangerous stuff. So let's go ahead and we'll enable our contactor. And you can see it's roughly 12.9 milliamps. You can see the smoke rolling off of it. So for fun, let's just see what the resistance of this is now. Looked like it was changing. And you can see it's now 91k ohms. It's starting to cool. You can see the resistor starting to go back up. Here we have a 10k ohm resistor. So again, 10k times the 10 meg divided by 10k plus the 10 meg gives us 9.99k ohms. And 1000 volts divided by our 10k is 100 milliamps at 100 watts. So for 100 watts, we're not actually going to try that with that little resistor, but this is really what we need. So you can see this is a 10k ohm, 225 watt resistor. Alright, this should be roughly 100 milliamps at 1000 volts. There you go, 950 volts and 92 milliamps. So where's the rest of the drop coming from? Well, there's two things. One, I have a HRC fuse in line with this power supply, so that's got a little bit of resistance, and I also have a small series resistor. So essentially, if anything shorts out, I'm going to limit the current back to that power supply. As you can see, that was basically 100 milliamps going through this 10k ohm resistor. So this is my model for the Fluke 87V. This is similar to a lot of the meters that I look at, in that there's a single resistor, and that's in series with the PTC, and then in line with that is our high-speed clamp. Again, in these cases, the 1K resistor is pretty typical, and so is the 1.3K PTC. And again, we just have a simple clamp out here that'll typically clamp at about 8 volts. So what I have here is an Ohmite 2500 ohm resistor. This one's rated for 10 watts. Again, at 1000 volts across that 2.5K, this will be 400 milliamps from the power supply, or roughly 400 watts out of this 10 watt resistor. This resistor is just going to go up in smoke really quick. So what I'm going to do is just pulse the output. So what I have here is our high voltage probe, and that's attached to the output of our power supply along with our Bryman BM869S. And this attaches to our oscilloscope, and this is currently 500 volts per division. So when I pulse this, this is 100 milliseconds per division. So this is 0.3 seconds or 0.5 seconds here. And if we look with the Bryman, you can see it's basically 500 volts. So what I'll do is turn up the power supply a little higher, and there you can see we're at roughly 1000 volts. You can see we are now 2 divisions up, or 1000 volts. So again, This resistor could actually come apart. I really don't know. That's a fair amount of current to be putting through this device. So we're going to go ahead and install it inside of our little box here. Alright, here we go. 3, 2, 1. You can see our power supply starts to sag a little bit. There's also some transients. Again, those are caused by the contacts. I'm just using a mechanical contactor. Obviously, that's why you can hear it. Looks like the resistor survived just fine. These are a few PTCs that have came out of the meters that I've damaged over the years. Typically in the cheaper meters, this is what I'll find are these very small PTCs. Typically what will happen is these will break over and it'll actually blow the casing apart. A lot of meters failed that way. Again, this is my model of the Fluke 87V. There you can see the difference in the size of the PTC that we're using. So what I have here is just a 1K resistor, and then I have one of those small PTCs. Look over at the Bryman, you can see it's 1K ohm roughly, and if we look at the PTC, that should be roughly 1.3K. You can see it's 1.22. You can see I have the PTC along with our 1K ohm resistor, and again this is attached directly across the power supply. Now the Bryman meter on the right is looking at the voltage directly across the PTC. The other Bryman is looking at the current through this network. Alright, I'm just going to go ahead and enable the power supply. What I'm going to do now is start to turn up the power supply very slowly. About 130 volts right now at 5 milliamps. And here's 200 volts at 4 milliamps. And here's 300 volts, roughly 3 milliamps. It's about 500 volts. You can see the current continues to drop. It's about 1.7. Alright, and here's roughly 1,000 volts. And you can see the current is now all the way down to 1.36. And you can also see basically all the voltage is being dropped across the PTC. Very little voltage is being dropped across our 1K ohm. So let's let this network cool down a little bit. Again, the resistance will change as it heats up, and then that limits the current. So the PTC isn't going to have time to respond. It's got a lot of thermal mass, and so with that sharp edge, we're going to get a lot more current than just a few milliamps. This is going to be closer to, you know, several hundred milliamps. And what we'll see is if this thing comes apart. And I think before we do this, let's just tuck it up under our window, just in case. Looks pretty good. You can see it just about in the center of the picture here. Alright, here we go. So it does not appear that that broke it. Again, this is the pulse off of the oscilloscope, and we are still at 500 volts per division. Let's just give it another transient. I'll hold it on a little longer. I think our problem here is the PTC is just going to get hot, and again the current will come right back down. So that network seems to work just fine. You can see there's no signs of any cracks or anything in it. Alright, so this is the first meter that we're going to look at. Again, this is the free one that Harbor Freight supplies. Now this meter is actually the one that I did the switch cycle testing on. You can see all the dust. And then I exposed this to my ESD gun. This was actually the only meter so far that gun is actually damaged. You can see it still powers up. But if you put it in resistance mode, for example, you can see it's reading 9 ohms. This is in the 2 mega ohm. You can see it's running 115 k ohms. I'm not sure if this will actually read voltage. I've got our Harbor Freight meter attached to my power supply. You can see it's in the 1000 volt setting. What I'm going to do is just turn on our power supply and you'll be able to see the voltage over here. And let's just see what voltage this Harbor Freight meter reads, because I'm pretty sure this thing will actually maybe even work. Nope, 234 volts. Of course, the Bryman's reading roughly 1,000. Let's try it in the AC mode. You can see it's reading 50 volts. That's with nothing applied. So what we want to know is in the resistance mode what happens with this. So there's enough energy with this power supply. I don't want to be rotating the knob while I'm actually running this test. So this is similar to running that half cycle simulator. Basically I want to set it up, throw the contactor and just let it do its thing, and then shut it off. Let's go ahead and we'll give it a try. Wow, that was it. It's saying low battery. You can see it's got quite a few burn marks. There's one here. There's one up here, here. This device here is burned. Again, that isn't anything that the switch cycling has done, nor is it anything that that ESD gun would have done. Let's have a look at the back side of the board. You can see right here, right where the main IC is, you can see how it's lifted just slightly. This switch, of course, didn't get the full 50,000 cycles. I aborted the test because it started to open up. But again, with this meter, you can see there's no PTC whatsoever. So you can see this meter uses a glass fuse for the current. Oh, there you go, 2.4 ohms. So that fuse is in good condition. There you go, 0.42 ohms. Yeah, I think there's one last test we could run with this. Early on in this testing, I get a lot of different comments from people. I don't know, lack of education or something, but people would comment about me putting DC into these meters. That's kind of the whole definition of what I'm doing. It's transient testing, it's not DC voltage testing. So now, those of you who are accusing me of putting DC into these meters, I guess you're going to have your way. So you can see I have the meter in the 200 milliamp range. Now again, I'd mentioned previously that I have a series resistor in line with this power supply, along with a safety type fuse. So when I do this test, I don't expect this to be near as violent as what we get with that half cycle line simulator. Let's just give it a try. Let's just try one more time. And you can see the fuse is definitely opened up. Obviously I blew the fuse. I'd say that's probably your shunt. Well, I think that's about all we can do with this meter. This is the other meter that I had purchased to do the life cycle testing with. These are the original contacts, so I had replaced those. This meter is actually 100% functional right now. So let's try the same test with this meter. But I think before we do that, let's go ahead and take this one apart. Alright, so on this particular meter, when you put this thing into resistance mode, let's just pop the batteries out real quick. So this is the voltage input here. You can see that goes straight to this PTC. So the problem with a meter like this is there is no high surge resistor. That PTC's got to handle that full 1000 volts across it. So it might actually be able to take it if I creep up on it. It's hard to say, we'd have to give it a try. But I'm pretty sure that if we just go ahead and turn it on really quick, it would probably destroy this meter. So let's try it really slow first. Let me go ahead and put it back together. We'll leave the battery in it. Let me just show you it working. So this is going to be a 10 mega ohm resistor. See 10.03. This would be 100K. This is a 1K. This will be 50 ohms. Let's just try it in diode. Well, there's continuity. There's diode check. And this is our DC volt, so this would be 5 volts, 2.5. It should be roughly 60. AC volts. This should be 2.5, and this should also be roughly 2.5. This one's DC coupled. Try it in frequency. So there's 30 hertz, 15 hertz, 120 hertz. So the meter itself functions okay. I had saved it all this time for running another test, so this would be a good test for it. Alright, let's go ahead and turn on the power supply. See, the Bryman in it reads fairly close right now, about 7.5 volts. Let me go ahead and switch it over to resistance mode. And now what I'm going to do is just slowly increase our supply voltage. And again, the meter may actually survive this test. Just bring it up nice and slow. Tell you what, are you kind of wondering what the current is? I am. Let me just set up the other meter. Okay, so the meter on the left again is looking at the current. Let's go ahead and turn the power supply back on. So it's roughly 2.5 milliamps right now. Oh, so there you have it. You can see the meter is now switched over to the millivolt range. Yep, every range in millivolts. See that? Alright, let's have a look. Well, you can see it just blew the back right off of the IC. It looks like the PTC is still in play though. I'm actually kind of surprised that it displays anything with that IC blown like that. The next meter I'd like to try is this Uni-T UT90. This is one of the original meters that I purchased out of our $50 shootout. Out of all the meters that I purchased, this meter has probably been damaged the most out of all of them. At least more often. The last time I damaged this, somebody had posted that basically I should just go ahead and throw the thing away finally, but I went ahead and rebuilt it anyway just to prove that I could, because on this meter what ends up happening is there's just not enough clearances and the meter will flash over. So then it gets this huge current draw through it, and then it'll vaporize all the copper, but it never makes it as far as damaging the control IC. So it's not that this meter is any more robust, it's actually a crappy design that's making it survive. I've seen that with other meters, and it's funny because people will comment, oh, that meter made it to, 4 kV or something. Well, yeah, it's because, the frickin' meter's breaking down on the inside, and it's basically acting as a, a spark gap. Fortunately, I was turning up the power supply and nothing was happening. It looks like we damaged the HRC fuse in the meter. Now, I have another fuse that's upstream of this one, and unfortunately, it was the one in the meter that took the abuse. Anyway, this is still the original meter that I purchased way back when. The one on the right's the one that Bryman had sent me for the life cycle testing. This actually does not have a good battery in it yet. I'm running out. Typically what ends up happening is this meter gets all the old batteries from the meters that I damage. Alright, so hopefully now we'll be back on track. Again, these fuses here are rated for 440 milliamps. They're 1000 volt AC/DC rated at 10 kA break current. I have, I think, 3 of those left. So hopefully we won't burn another one up. But unfortunately what ends up happening is if the meter arcs, it's going to draw a fair amount of current. Of course that's either going to blow the meter's fuse or the one that's in line with the power supply. Alright, you can see we have roughly 130 volts or so applied at roughly 7 or 8 milliamps. Again, I'm just going to slowly increase this. It's 500 volts right there. See the current's going down slightly. 3 milliamps right there. I think it's beeping because it's more than the 600 volts. There we have it. It's 1000 volts. You can see roughly 2.7 milliamps. Alright, let's get our test box out. So again, this will be a 10 mega ohm resistor. You can see the PTC got a little warm. Looks like it's settling back in. This will be a 1 mega ohm resistor. Spot on. This will be 100K. And this will be a 10K. This will be a 1K. Pretty impressive, huh? And here's 100 ohm. Not bad when all the stuff that this meter's been through. It's probably the only meter that's ever played any Van Halen music before either. Alright, again, this will be roughly 60 volts. Let's see, 61. Let's try it on the 200 scale. 60.6. Looks good. This will be roughly 5 volts. Looks good. Let's try it on the 750 volt AC scale. This will be roughly 70 volts. This is on the 200 volt scale. 71. Of course, this is not an RMS meter. It's on the 20 volt scale. This should be roughly 2.5 volts. And this should be 2.5 volts as well. Again, these are square waves. So yeah, the meter looks like it's still fine. So now what we'll do is apply our 1000 volts with the PTC's cold, and let's see if we can force enough current through the meter to damage it. And 1000 volts. You can see it dropped right to 3.3. Alright, let's check it again. We won't go all the way through it, but this will be a 10 mega ohm resistor. Again, it's quite hot, but looks like it's cooling down just fine. This will be a 1 meg. Looks good. Let's try it with a 50 ohm. Looks real good. So no problems at all with the Uni-T UT90A. Looks like this meter isn't going to the recycle bin anytime soon. Alright, so the last meter I want to test is this Fluke T6. Again, this is the 600 volt version. I had damaged this meter earlier, but again, I've repaired it and it works just fine right now. So I've got this currently connected up to our high voltage power supply. Let's go ahead and turn it on. You can see I'm putting out roughly 3 volts into it. Let's just turn it off and try shorting our leads out real quick. See, it's reading 1 ohm. No problems at all. Somebody had recently made a video about this meter. They were talking about troubleshooting some system that was at 24 volts. I had to kind of chuckle because they were talking about that, and then they were explaining how, you know, testing these meters on the bench like what I'm showing is not real world. To me, it's all pretty real. I mean, I'm putting 1000 volts across the meter, and I've got a power supply sitting here that can obviously put out more than 400 milliamps. I mean, that's pretty real. You don't think that that could hurt you. Anyway, the other comment that they had made was, you know, that all these switch positions could get confusing. I'm thinking, man, you know, look at this Bryman BM869S. Shit, you got all the buttons up here, plus you got all the meter position switches. How the heck would you ever figure out how to run a meter like this? Alright, so let's go ahead again and we'll switch this to ohms. Turn on the power supply. And again, I'm going to creep up on this. You can see it's already detecting the high voltage. So there's 70. There's 100. Look at the current. can see it's heating up. It's 16 mils. Again, the PTCs that they use in the Flukes are quite a bit larger. They have a lot more thermal mass, so it takes longer to heat them up. Of course, they have a side benefit, and that's that they don't break down at low voltages. Of course, I say that and watch this thing break down. And this meter is only rated for 600 volts. And there we have it. Alright, let's give it a quick check. See, 0 ohms. Again, this meter can't read up very high. This will be a 1K ohm resistor. There we go. 1K ohm. And this will be 100 ohms. And here we have 50 ohms. So no problems at all. What I'm going to do is connect this back up to the power supply. What we'll do is just go ahead and again close the contactor and apply the full 1000 volts across the meter with the PTC cold. And let's see if the Fluke will survive this. Doesn't seem like anything broke down. Alright, again we'll short them out. See, the PTC is a little hot. It's going to take a little bit to cool down. Again, this will be a 1K ohm resistor. This is 100 ohms. Dead on. Here's a 50. Dead on. Here's with a 1 ohm. I don't have anything between a 50 and a 1. Again, this is our 1K now that's cooled down. See, it looks fine. So no damage. Again, in my opinion, the big problem with this meter is that it's sensitive not so much to the location of the wire, but certainly to the wave shape. You know, I can understand this thing having to sit down in the pocket like this. It's called out in the manual, and the fact that, you know, I can test this thing and have it be, you know, about 1/8 of an inch away. That's plenty sensitive, I think. I've had this thing out in the field with me, trying it on different loads, and, you know, it actually did a pretty decent job. I just don't like the fact that some of the waveforms that I test, again, that this thing can't detect them. The ground indicator will turn off, but it just can't display any voltage, even though there's high voltage present. Again, this isn't a test that I'm going to repeat in the future. I just thought I'd give you some idea if that insulation tester that Voltlog had used, you know, to test the little pocket meters was actually capable of putting out, say, an amp at 1000 volts, and he had applied that to those pocket meters. I think that more than one of those would have lit right up. So that's going to be it for this video. Hope you enjoyed it. Till the next video. Later.